All right, so yeah, constraint types. What do I mean? So first we're going to show what programming looks like without constraints. So we have a divide function that we've created, and it's going to take a dividend and a divisor, and it's just going to divide them. And we're doing integer division right here, so we don't have to worry about remainders. So for example, when we divide 7 by 2, we get 3, because it's 3.5, and we just discard the half. But this method isn't entirely safe because someone might call it like divide 5 by 0, in which case they'll get an arithmetic exception because they've divided by 0. Another problem someone might have is they divide a negative 2,147,483,648 by the negative 1, and they get this, they just get the dividend right back out, right? Because we have overflowed. So these are like things we don't want people to run into. So how do we prevent this? So if you want to enforce these constraints at runtime, it's actually quite simple. You just can write an assertion, put your computation in there that you don't want to happen. I mean, the problem though, right, is that we're still hitting runtime errors. So the divide 7 by 2 still works, but when we do the other two, we can get a runtime assertion error for, the overflow now gives us a runtime assertion error as well. Is that better? I don't know. Up to you to figure that out. So we have that for runtime enforced constraints, but what about compile time enforced constraints? So over the years, there's been much effort focused on something called like refinement types. And in Scala, they've kind of worked by wrapping up types with like tags or smart constructors. So when I say wrapping, I don't mean like the wrapping with maybe a runtime cost. I basically mean the types are wrapped up, so they're not the same type anymore. So here are just some examples of libraries that do this kind of approach. If refined is probably the oldest one. I wrote one in graduate school that nobody uses. That's including myself. I don't even use it. So, if you are going to use one of these libraries, don't use mine, right? Use one of the other ones. But those approaches have some weird things about them. So here's a refinement example of kind of how these systems work. So right now it's underconstrained, and how it works is it takes divide. The dividend is still an int, but the divisor is an int and a non-zero, kind of like a tag is what we usually call them. It's like an empty type that has some implementation associated with it. And so now, due to like some implicit conversions that usually these libraries perform, it'll prevent us from doing something like dividing 5 by 0. But we still have this problem of dividing a min value by -1. And so the question is, how do we remove that? How do we remove that constraint? Does anyone have any ideas how they might go about that? Just I want you to be thinking about that. So we might be tempted to do something like this, where we now have tagged that, hey, we can't have the dividend being the min value, and we can't have the divisor being a -1. But that also has consequences where it's over-constraining our options. So that bottom example is probably the one that's the most problematic. We now can't divide 4 by -1 because these are mutually like dependent constraints, right? But we did catch the divide min value by -1, so that's good. But now we're being too restrictive. And so like how do we do this? So here is what I was used to preach, and I feel bad about it. So here we now have divide, and it's taking like an operand. So we've tupled up the arguments, and we've like added another tag on top of that tuple. And then we have like extractor tuples to get the first part of that tag out, and then like the second part, And now when someone calls this method, they tuple up their arguments. And like, I remember when I used to say this, give this like presentations on these type of systems, I would say something like, this is just something you have to do if you want your code to be safe. And then my response to myself during one of these presentations was like, well, then it's not worth it. Like, this is ugly, this is gross. And it was in the middle of a presentation, like kind of preaching this, that I'm like, this is never going to catch on, is it? Because I just think this is really ugly. And so what a traditional refinement system, I call these traditional refinement systems, in Scala community. So they're good at many refinements can refine one value. For example, you can have an int that's positive and even and divisible by 7. And that works nicely. You just keep tagging on these constraints. But one refinement cannot elegantly, I'll say, refine many values. So we can say inelegantly, that's what we saw in the last slide. But for example, if you want a constraint that 3 numbers are in increasing order, it's not very elegant because they're mutually dependent on each other. And so my question was, what system allows many values in one single constraint? And so this is what I've come up with. And I don't know what to call it, maybe something like Singleton constraint typing. And it looks a little something like this. So you have our divide method. Its parameters, dividend and divisor, stay the same. They're untouched. But now we have another parameter list that has all the guarantees that we need to provide in order to call this divide method. This guarantee type is kind of like your evidence that you have satisfied the constraint. And then there's a couple type combinators, or like those are actual constraints. So I won't show the implementation of those here, but those are kind of the types we need to define, to specify what our code should look like. And now for comparison, these were what our runtime constraints looked like. And they look extremely similar. You don't have to jump through these hoops of wrapping your types up and repackaging them. You can stick with kind of like the normal computation like signatures that we have for our runtime comparisons or runtime constraints. So how does this work? So you can get guarantees in different ways. So here we're dividing 6 by 3, and we can get these guarantee types. One example is by guarantee.verify at compile time. And it's able to see the dividend and the divisor's type being 6 and 3. And it kind of plugs those into these guarantees and it compiles because those guarantees are not violated. But how does this work with unknowns? So let's say we try to divide a random int by 3. Now, should this compile? Well, if you think about it, the non-zero divisor, we have to guarantee that the divisor is non-zero. And so we can call guarantee.verify at compile time, and that will check out because divisor is not equal to 0, it's 3. It can see that. But what about no overflow? So the no overflow, we can also call verify at compile time because it'll try to plug in dividend. It'll notice it's just an int, like a random int. So that's not going to work out. The dividend type not equal to min value isn't going to work. But since it sees the or there, it knows it can try the other side. And it will plug in 3.type 3 into divisor.type, and it'll find that that is not equal to a -1. And since that satisfies that part of the or, the entire or constraint is now satisfied, and this allows it to verify. Now, what if we're trying to divide like 6 by an int that's in a range of 2 and 4, so it could be either 2, 3, or 4. Now, our type system isn't going to, we don't want to teach like our constraint system what random.nextInt is, right? That's a rabbit hole you don't want to go down. So what we can kind of like, there's a backdoor that called guarantee.trust. And one way we can get a guarantee is just like, hey, just believe me, You don't have to check it, just believe that this is going to work. And that's what guarantee.trust does. And then we can still verify though the no overflow but at compile time because we have that 6 as the numerator, and it plugs that 6 into dividend.type, sees that that's not min value, and we are able to check that part at compile time. What if you don't have the divisor at compile time, you're getting it from the user? Well, in that case, there's no way that you're going to be able to guarantee at compile time that it works. So we have a guarantee.test at runtime. And this is going to return an either. So you put in your predicate, your like Boolean predicate that you want to check, and it's going to check that constraint. And if it's successful, you'll get a right, and that right side is going to be the guarantee of what you wanted. And so in the right case, we're able to divide 6 by divisor, and we pass in that guarantee. We can still verify the no overflow because we see the 6 there. But in the case of left, we actually get the inverse guarantee. And in that case, well, we can't call divide. We don't have the guarantee. So we're going to have, whatever we put there, it's going to have to be something else. It's not divide. That won't work. And so, well, it would be convenient or elegant, to not have to pass in, or not have these guarantees show up when they don't need to. And you can do this by making these like implicit guarantees. So these examples, dividing 7 by 2, it's going to compile because it'll try to find these guarantees. And by default, that will use the compile time checking. The next one, dividing random int by 0, that's going to be a compile error because it sees 0 is, 0 is 0. It's not non-zero. And then dividing min value by random int, that's also a compile error, but that's a compile error because it's unknown, right? It doesn't know if this divisor is going to be -1 or 0, because if it is, then it's going to be a problem. But we can still divide like random int by 5, because there's no way that that dividend can be a value that's going to break this program. And I put the ellipses by implicits because I don't know if this is actually a good approach, but it looks nice, right? Your code looks the same. But now you might run into situations where you have multiple guarantees of something holding. And do you really want to get an ambiguous, implicit for that? You don't. You don't care. You're like, well, just use one of the guarantees. I don't care which one you choose. So I'm not certain if this is like the right way to go, but there are situations where you kind of have to do this. It's usually around like type classes and stuff. So the idea behind singleton constraint typing is the method signatures remain the same, other than you add this parameter list that has all your guarantees that you need to hold. And they can be obtained in one of 3 ways. You can get a guarantee by checking at compile time. You can check it at runtime, or you can just leave it completely unchecked. And those are the only 3 ways, right, to get a guarantee. And so what are like the scope and goals behind like a constraint system like this? And the idea is we want any computation that you can think of could be turned into a constraint. And we want that constraint to be able to be checked at compile time. Like, how is that possible, right? So that's the goal and scope of this system. And we also want constraints to compose with each other. And I think that's a pillar of, at least for me, of programming, is things have to compose together to solve bigger problems. And I guess I'll point out that I should say that like inference is not a goal of this system. It's not trying to like infer that, oh, if an int is greater than some value, it's also greater than a smaller value of that. That's kind of like, it's like a non-goal, not because I think it's bad, but because it's a rabbit hole that when you're trying to support custom constraints, it's easy to get lost. And so here's like an example constraint that we might want to migrate to compile time. So right here it is at runtime. We're trying to get a character out of a string by its index. So S is the string and I is the int, and we have to make sure it's in a valid range. So it has to be greater than -1, and and it has to be less than the length of that string. And if it is, then we'll go ahead and call s.char at I. So example, char at abc at 1, it's going to return b. It's the middle. And then if we try to do char at abc 5, we're going to get a runtime error because it's out of bounds. So we don't want to have runtime errors though. So how can we move this up to compile time? And so we kind of move that assertion into a guarantee. So now we call it within bounds, and it's a guarantee that -1 is less than i.type, and i.type is less than the length of s.type. So it refers back to the parameters or the function. And so the idea is we want to work like char at ABC of 1. That will compile if we try to verify it at compile time. And the char at of ABC of 5, we want that to not compile and give us an error at compile time. And so how can we make this work? Well, we need a couple of constraints. Length is one that we can see up in that guarantee. And we also need this less than constraint. We're going to implement the length one just so you can see how it works, and then you can go home and you can implement, the other one when you have time for homework. So how can we teach this constraint system about length? First, we need to implement this type class called compute, and it has some C type, which is the constraint, and then in its body we have the result type, and that's a type and it's not in the parameter list because we want it derived from the constraint type. And then we can call like compute to get the result. And so if we're trying to implement this for length, we just say, hey, given some type S, if it's a string, and if we can get the value of that string at runtime, that means we have a compute for length, and the result type is an int. And the way compute works is it just calls value of that type S, and it calls .length, just like a normal function. And now we've encoded what that length constraint means to runtime. So how would we test this? So we can do like val result of type int equals compute length ABC. And then if we test assert result is 3, that's going to pass at runtime. So this is good for runtime, but how can we check this now at compile time? So it's also just an interface that we need to implement. Call it inlineable because I don't know of a better name. And it also has a result type, but it's different than the runtime computation because this reduce method, it is now inlined. So it's going to run this code at compile time. And now we're not getting back a result, we're getting an option of the result because we might not actually be able to definitively tell what the result is. We might not know. It might be unknown. So this is kind of like trinary logic or ternary logic. And so now we can implement this length. And the way we're going to have it work is we're going to call into a macro. And so that's what that, override, transparent, inline def, a lot of keywords. But the implementation is now provided right here. And it's just one line. It's where we call this helper called from computation, and it'll try to take a value out of that S type. And if it can, we're just going to go ahead and summon that runtime computation type class instance. And that keeps it consistent. So usually, or often, you implement these compile time checks by reusing the runtime checks, just so they stay in sync. But you don't have to do that, but that's usually what I do. And so how do we actually test this? So now, if we do like a transparent inline def, inlineable, we're going to summon that inlineable instance for length of ABC. Now, if we call reduced equals inlineable.reduce, we can actually see at compile time, if we try to type that as an option int, it's going to work. But we can also type it as a sum int, so it knows that this actually is not going to be unknown. That is actually known. But we can go further than that, and we can actually type it as a sum of 3, and it knows that it's going to be the number 3. And if you know that much, well, then you can actually just inline it with .inlined. And you can, if you try to treat it as 3, it knows that will work out. And if you run this code at runtime, you are going to get a 3. So it's not just some backdoor. You're actually getting the result 3. And so sometimes a question that I have had about constraint systems for myself and others is it'll be like, can compile time checking work on like non-primitive types? So we've shown a primitive type here in string or int, but does it actually work for like data types you write yourself? And it does, as long as you expose the primitive values that like all data types are made out of. Like all data is made out of primitive types, right? And So this question, I think it's actually asking a different question. And I kind of want to explore, why sometimes we think this kind of thing doesn't work for like our custom data types, because it does. And I think it requires maybe a paradigm shift from black box to white box, like data representation. So the normal data we usually see is like a black box. So let's say I do like val I of int equals 7. That's the same thing if someone did val I equals 7. So if someone does something like that, if they later try to treat that as an int, it's going to compile. If they try to treat it as a 7, we get a compile error because it has forgotten the value with which it was initialized, right? We can learn that fact at runtime through like assertions, like asserting as 7 is going to pass, asserting as 3 is going to fail. But we can't know that information at compile time. But if we model our code differently, our data representation, for example, saying val I of type 7, and then in order to not repeat ourselves by putting a 7 right here, we use value of. Or if we do inline val I equals 7, those both retain information about the values they're initialized with. So if we try to treat it as an int, that's still going to work because int is a super type. And if we try to type it as a 7, that's going to compile as well because it remembers that it was initialized with 7. And it also will give you a compile time error if you try to treat it as something it's not. So I of 3 is not going to work. This kind of goes back to an old quote I thought of a lot by Dijkstra. And he says, but as long as we regard the mechanism as a black box, testing is the only thing we can do. The unescapable conclusion is that we cannot afford to regard the mechanism as a black box. i.e. we have to take its internal structure into account. And so when we want to compare, we want to check our code at compile time, we have to start showing, like, we can't hide it behind a black box. We need to expose it, or else our compile time checking isn't going to work the way we want. So this is from a report called A Concern for Correctness as a Guiding Principle for Program Composition, which I love because it talks about correctness and composition, which are my two favorite topics when I'm thinking about how to structure code. So let's look at an example of what I mean by like a data type with internal structure. So let's say we have a fraction. A fraction has a numerator and denominator. And in order to create a fraction, we have to pass in a guarantee that the denominator's type is not 0, right? That's just by definition how a fraction works. And now if we try to get the whole number part out of it, for example, if we have a fraction of 7 and 2, we verify that the denominator is not 0, and we try to get the whole number part out of it, we want to get a -3, because 7 divided by -2 is -3.5, and -3 is the whole number part. Now there's an error. Can anyone see the error in this code? Does anyone see it? So since it's hard to see, I think that helps make my point. What if we try to divide a min value by -1 right here? We're going to get an overflow, right? But now here my question is, like, does this code even compile? And it depends on how we structure divide. If our divide needs guarantees, then this code won't even compile because it's expecting you to pass in guarantees. So how do we get these guarantees? Well, it turns out we have a non-zero denominator that matches the guarantee of divide not being 0. And so we can actually reuse that when we're calling divide. And now how do we get a no overflow guarantee? Does anyone have any ideas? I want you to think about it. Like, we need it somewhere. Go ahead. So yeah, so if you put it up in the constructor, so that's one approach. But now what if you want to create a fraction that's the min int over -1, but you never want to call whole number part? It kind of precludes you from being able to construct a fraction like that. So you need like ad hoc guarantees. So you want them, if they call whole number part, that's when you actually want that guarantee to be passed in, just so you don't prevent people from creating fractions and not using the functions that they don't need. So now we'll have both guarantees that we can pass to divide, and that works out. But how does this actually work in practice? So currently fraction is a black box. So if I say val fraction equals fraction, some random int and 2, and we're trying to verify the denominator, that's actually going to work. So this is, compiling code. But now if we try to later call fraction.wholenumberPart, we're going to get a compile error. Even though no overflow, like knowing that it's the denominator is 2, that should check out. But we've forgotten that we've created our fraction with a 2 as the denominator. And so we want to remember that information about how we construct things. And so this is kind of the idea is what if our fraction wasn't just a fraction black box type, but it was some like refined type where the fraction is val denominator is not just an int, but it's actually a 2. And in that case, we have to kind of cast it here, to convince that this is how it's going to work. But now we actually are able to compile the .wholenumberPart because it has remembered that it was constructed with a 2. But this is kind of ugly, repeating ourselves right here, this 2 and this 2 and casting right here. But we can like put this behind it a nice API. So in this case, a fraction, we have a companion object where we can just define this type alias, which isn't necessary, but I think is nicer, where the values actually become types, and we refine that. And so now when someone calls like fraction.apply, instead of getting a black box fraction out, they're going to get a black box, or they're going to get a fraction like a white box. So they're going to be able to remember and see the values they've constructed this with. And so now this is identical usage for the user, but now everything compiles because fraction remembers that it was constructed by a 2 denominator down here, right? And so summarizing the key ideas behind this approach is we want to associate constraints with values rather than wrapping those constraints around our values. Because when we try to do that, it influences the rest of like the code that's trying to call that. If we want to just learn something about a value, we shouldn't need to change that type. We should just expose the value that it actually is so that later on we can remember that value and use it for our constraints. And I think the other idea is we want to have ad hoc constraints, and that is only possible if we expose our values. We don't want to go back in time where we want to call a method like way far away from where we constructed the value. And if that value is like black box, we don't know, we have to then go back all the way to the code to where we've initialized it, and we have to change the types up there. And we want to avoid that. We want that value when it's instantiated, just exposed to the rest of the world. This is the actual value I hold. And then later on, we don't have to go back in time and change that initial type because it's just telling us honestly what it holds. So this is the repository where we can check out how this stuff works. There is no official release, and the documentation is maybe even misleading in the Scala docs. But I mean, that's not how I hope it'll be for the future. My idea is to try to release something like this by the end of the year that's actually usable. And I've been working on this for several years. And so I think, it's actually pretty close to production ready, other than, the missing documentation. It's a sound basis for building upon. So yeah, ended kind of early, but that's all I got. So open it up to questions.